I've got eyes on it to see when it pops up.
It looks like we're live. Not yet. It says we're live.
Let's see if I can.
There it is. I see it on my end. Let me know when you see it, Angelica.
Maybe I'm just looking in the wrong place. Videos. Maybe you could ping me the link.
Yeah, I just sent it to the Tiny Tech Go channel.
Oh, awesome. I can jump on that.
So it's there, and then we can share it out to the masses. Let me stop. I got video going in too many places. So we pause the stream. All right.
Boom, I can see it.
See it?
Yep.
Perfect. All right.
We
awesome.
Officially live and with the masses.
So I'm just going to move people back to attendees to get things going. All
awesome.
right. And we will start the show.
You ready? You good?
I'm always ready. Angelica, you good? Let's do this.
I'm always ready. I'm very, very excited. I want us to have some kind of theme tune to start our events. I've been on GoTime too much. Now I'm like, I need an intro track. Maybe I'll work on that. If anyone who's already jumping on, who's obviously an extreme keen bean for our GDN events, if you'd like to create a little jingle for us, I would not be upset. Ping me. Awesome. So welcome everyone. We're extremely excited to be starting this, which is our third GDN event, Tiny Go Technology and Hardware. This event will cover a range of different topics from a range of wonderful different gophers from around the world, diving into the world of tiny technologies, hardware, and microcontrollers. We're going to be talking about working with Tiny Go, Arduino, MicroPython, as well as our lovely speakers demoing some of the awesome projects that they've been working on. All of the chatter, all of the questions we'll be fielding both in the YouTube channel chat, as well as in Gopher Slack in the tiny_tech_go Slack channel. I will be posting this on the YouTube channel so you can kind of redirect yourself for more chatter there. Without further ado, I'm going to introduce you to my wonderful partner in crime, Wilken, who's going to be telling you a little bit more about GDN in case this is your first event with us.
Awesome. Awesome. Well, thank you, Angelica. I feel like I really don't have much to say. You said it all. So, but welcome, world. Super happy to have you here again for our third event. It's always a pleasure to have new speakers and a lovely audience join us. For those joining us for the first time, welcome. We ask, all our questions are threaded in Slack and in the YouTube channel. So if you have a question, please feel free to ask it. And if you feel like you don't want to ask it in a public space, you can hit us up directly on Slack. I'm Wilken Rivera and Angelica is Angelica Hill. So feel free to ping us directly. With that said, a little bit about the GDN or the Go Developer Network. It's an organization that started a few years back between GoBridge and Google as a way to sort of bridge, as a way to promote the Go community and the meetups around the world, right? So we do offer services like setting up meetups in your local communities and services for mentoring and various training sessions. So if you're interested in being part of the GDN, you can check out gobridge.org/, you can check out gdn.gobridge.org and we'll have a nice little write-up of who's involved, our mission statement, and how to contribute to the organization. Friendly group and always looking for people to join. And if you're new to the Go language, this is a good opportunity to meet people within the community, get some good resources on how to get started, and then build up that network. So that's the GDN. I'm Wilken Rivera. I'll be your host, your co-host today, and looking forward to having this next few hours with you. So welcome. All right, Angelica, back to you.
Awesome. So I have the pleasure of introducing our first speaker, Tobias Thiel. He works as a technical lead and DevOps for a German fintech startup, and has since 2020 also worked for RegTech, which is a startup Clarilab as a lead software engineer. Being a software architect and an expert for Go and TinyGo alongside C# and Java, he's also ISA QB certified. Teal is a highly enthusiastic community contributor and is among the top 10% of responders to the C and Unity 3D, as well as the top 20% responder in .NET, Go, and Visual Studio on Stack Overflow. So I think a highly enthusiastic contributor may be an understatement. He is always there to help. When not programming for Fino or Clarilab, he can be found developing games, mainly at game jams such as Ludum Dare Jam, where he develops games from scratch within 72 hours. As an active speaker at Tech Talks and a participant in numerous hackathons, Teal also loves to share his knowledge of software development with fellow enthusiasts. And we're very, very lucky for him to be sharing his enthusiasm for TinyGo today. So I'm going to pass it over to you, Tobias, to kick off your talk. Hello, Tiny Gophers.
Hello, everyone. Thanks for the very nice introduction. And I guess everyone heard a friend of mine, a marketing dude, just wrote the text, more or less, for the introduction. So let me have a short check up here. Okay, that's still working. I want to share my screen. I guess. Nope, not this one. Maybe this one. This looks good. Okay, so I hope every one of you can see my screen. I guess that's the standard question every time when doing any conferences or Zoom or whatever stuff. So we are going to talk about TinyGo today, and I'm really honored to be the first one to start to bring you into the topic. And I thought I'd just start right into with a demo time. So I want to introduce you to a little project, to a little home automation project I'm working on in my spare free time. So lately, not so much because there is no free time at all, but I'm still continuing to work on it. So what do we see here? We have a web app and some buttons in here. And when I click here, something starts to blink around me. If I click stop, it stops. When I turn it off, well, it's dark in here. Yeah, I turned on dark mode in my room so I can see the blinking and the lights. So what is it about? Let us go one step back. So we have this really nice user interface here with some kind of login screen. And if I enter some data, well, that's wrong. If I enter some correct data with a highly secured password, 1234, I can sign in. And in the background, I'm talking to some MQTT broker to be able to make things blink in here. So now you wonder, what is it? What is blinking and lighting in here? I have some LED strip right here, which is connected to a microcontroller. I currently can't move it, or the cables are going to fall off. So I'm just going to leave it there. So we have some interesting home automation projects. I just wanted to showcase it as a start, so you got to see something before everything crashes down and stops working now. So let's get back into it, and we go back to the to this project later on again. So my agenda: what is TinyGo? Tell me about the features. How do you work with interfaces like GPIO, SPI, and so on? And we're also going to talk about WASM. So what exactly is TinyGo? In easy words, it's Go for small places like microcontroller, and also Go for WebAssembly. And in some more words, it's a new compiler for Go written in Go that makes extensively use of the LLVM compiler toolchain to produce binaries which run on lots of devices. So let us get some numbers straight. So TinyGo currently supports 62 microcontroller boards, which is huge. And the number is continuously going up. So it could also be that there are already new boards I have not seen yet. So the numbers rising all the time. And also we have at least 65 devices like temperature sensors or ultrasonic distance sensors or devices like this LED strips supported. And also here the number is continuously growing. So when talking about Go and getting Go onto a microcontroller, we have a little problem. If you have ever tried to write a really simple Hello World program and then just check the size of the binary, you see, well, we have a problem over there. So we have the easiest Hello World program I could imagine here. We're like 4 lines of code, just printing Hello World, nothing else. And when we compile it with Go, we have it results in about 1.2 megabytes of data. Just this 4 lines of code, more than 1 megabytes of data. Okay, hardcore. When we compile it using our TinyGo compiler toolchain, in this case, I used Linux as the Go OS. We only had a resulting binary of 0.04 megabytes. So you see, TinyGo, we have really small binaries in the end, and that's a really huge factor when we want to go to microcontrollers. So let's talk about features. Well, Go has such a nice thing called Go routines, and I can tell you Go routines are supported in TinyGo. Nice. Channels. When working with Go routines, most of us also work with channels to synchronize some data or get some data from one Go routine to another Go routine or something like that. So channels are also supported. Well, so TinyGo supports a big subset of the Go language. It supports slices, channels, interfaces, Go routines, the defer keyword, and also garbage collection. So more or less, lots of Go is just also supported in TinyGo, and also WASM and WASI build targets are supported. And now the question, okay, when so many things are working, what is not working? Not with TinyGo yet. This is caused by the fact that not the complete Go standard library is implemented in TinyGo. And some things had to be re-implemented from scratch, like reflection. And reflection is not yet completely implemented, which leads to some issues when trying to serialize or deserialize data, like JSON data. So more or less, lots of things that heavily rely on reflection might not yet work. But we can easily work around most of these issues. So now you might think, okay, I have somewhere in a drawer some spare microcontroller you have not used in the past 3 years, but now you know TinyGo and now you want to try it out. To find out if your microcontroller from your dusty drawer is supported, just go to tinygo.org and you are going to find a reference with a list of supported microcontrollers and also the level of support, like is SPI supported on my microcontroller, is ADC supported, and so on. Yeah, how do you work with interfaces like GPIO, SPI, I2C, and all these interfaces which exist in the worlds of microcontrollers? Well, let's have a look at the Blinky example I stole from the TinyGo documentation. The Blinky, this program is doing the following. It has a simple main function. We initialize a pin, the pin D4, name it LED, configure it as an output pin, and then we just run in an endless loop and just set the output pin to low and high alternating and waiting half a second in between. This makes the LED blink. So and you might have recognized there's a machine package. Doesn't sound familiar? Exactly. The machine package only exists in TinyGo. So TinyGo has an advanced set of the standard Go standard libraries. So if you want to talk to anything on your microcontroller, you can literally just import you have to import the machine package, and you'll find all the things you need inside this machine package. So we skip that for now. Also, you might know the Go playground. I have good news for you. If you don't have a microcontroller at hand and want to play around with some simple programs like the Blinky example I just have shown you, you can go visit play.tinygo.org and play around with the TinyGo playground in the web. Easy. So I want to start developing some home automation project or something like that in my free time, or some whatever microcontroller project. I have a microcontroller and some LEDs and sensors. Do I have to implement everything on my own now? The answer is luckily no. TinyGo got you covered. We've got an extensive repository with, I told you about 65 devices are currently supported in the drivers repository. There's a repository for Bluetooth support, a repository that helps you when you want to draw text using fonts on displays. We have the so-called Tiny Draw displays, which helps you to draw basic shapes on a display. There's a Bluetooth repository and so on. So no, you don't have to implement everything on your own, and you don't have to really search in the wilds of the internet for examples. For example, if you want to know how to use such an LED strip, well, you just visit a drivers repository and you'll find an example how to use such an LED strip. So TinyGo got you covered. Let's have a look at WebAssembly. So what's that? If you have not yet heard of WebAssembly, I have stolen the quote from webassembly.org. So WebAssembly is a binary instruction format for a stack-based virtual machine. WASM is designed as a portable compilation target for programming languages, enabling deployment on the web for client and server applications. Sounds complicated. Well, it's not that complicated. You could say WASM could be the future of web development and could also someday completely replace the need for JavaScript in the web. How's that? How's that working? So we can take Go code and compile it to this WebAssembly binary instruction format, and voila, we can run it inside a browser, for example. So you can have your Go code, your whatever, Rust code, and so on running in the browser using WebAssembly, which is really nice. So, and Go, standard Go already supports WebAssembly. Why should I use TinyGo for WebAssembly projects? Well, because the resulting binary size of TinyGo is much smaller than compared to if you compile it with the standard Go compiler. So again, a good argument is TinyGo provides really small binaries, and in the web you need small binaries, else you have, well, huge page load times and no one wants to wait for a website to appear. So let's go back to the home automation dashboard I'm building. So my goals are, I want to control LED strips, like turning off and on, change the color, let them animate something. I want to be able to turn on my coffee machine, for example. And maybe I also want to get the status of these thingies, and I don't want to stand up from couch, from bed, or from where I am right now. And also I don't have Siri, Alexa, Google, whatever. I don't have all these things. So, well, I'm just developing my own application. And as it runs in a browser, well, I can also just use my mobile phone. And when lying in the bed, I just pick up my mobile phone and, well, turn on my coffee machine. Sounds like a plan, I guess. So the architecture of itself. So that's me, that little guy there, sitting, laying in my bed, and open up a browser, visiting the URL for my WASM, for my WebAssembly application. And I have a file server running, which just throws out the HTML file and all other needed files. And then internally, this WebAssembly application is going to run inside of my browser. And the WASM app is going to do heavily chatter with an MQTT broker, which is more or less a service which allows you to send messages back and forth in both directions. If you have never heard of MQTT, it's a really nice messaging protocol. And also I have a microcontroller like the one controlling my LED strip over here. which also heavily chatters with this MQTT broker. So my microcontroller can send messages to the broker, which will then send a message to my WASM application and vice versa. So it goes in both directions. Yep. So the file server is really an easy one. I have just a typical file server which plainly serves the files. So I just initialize a new file server, let it listen on port 8080, and well, if it sees that a WASM file is requested, well, I set a content type to WASM. If it sees that a CSS file is requested, I'm setting the content type to CSS and just serve the files. That's the complete web server for my WASM application. So what other interesting files do we see when we initially visit this WASM application? So let's go to there, reload it, and let's have a look what we can see here. Well, more or less, we are asking for some MQTT JavaScript file, for some CSS file, for a WASM exec JavaScript file, for a WASM.js file, and for another MQTT JS file, and also for our index HTML file. That's it. So we have some files in here. So what are they doing? My index HTML file is pretty simple. I have more or less an empty body. It just holds a div for some content. I'm using the ID later on to dynamically replace the content, and well, I'm loading the JavaScript files and so on. So pretty clean, easy HTML file over here. Our WASM.js file has the role to initialize, to bootstrap our actual WASM application. So we're using this JavaScript to initialize our WebAssembly app and run it. So the WASM exec.js is pretty huge, so I only have a small part of it as an example. The WASM exec.js file holds more or less the complete implementation of the syscall.js API and maybe some additional stuff, but more or less that's it. So when you're calling some JavaScript functionality or whatever from inside your Go code, when you use the syscall.js APIs, your call is more or less going to land in one of these functions here. And the last interesting file is the WASM binary file, which, well, is not that easily human readable. The WASM file is more or less the compiled version of our WASM project. So this file here and all its dependencies compile to that gibberish. Okay, so how did I get to such more or less, from my point of view, a pretty nice, decent-looking front end over here when serving only a nearly empty HTML file? Well, I wrote a small library which I called TinyDom, and TinyDom is compatible. Is a DOM manipulation library which is compilable in TinyGo, and well, that was my first thing. There are lots of DOM manipulation libraries, but not all of them are compilable in TinyGo, so I just wrote my own. What does it do? It is basically a wrapper around the syscall.js API, because the syscall.js API does not have the prettiest API to use. I found it ugly, so I wrote my own wrapper to make it a little bit more pretty. And I also provide some custom types. And custom types like shortcuts to create form elements, images, input fields, and so on, and so on, and so on. So making my life easier when working in the web. How does a code look like to generate something? Well, let's have a look at this user input element. It's the one where I enter my username. All I have to do is create a new input. I set the autofocus to true, set an ID and a name, and the placeholder text. Done. Then I just have to append it onto the DOM, and nice, it's getting rendered. Also, how do we handle click events in here? Well, we have a button, for example, which needs a click event. Well, we just append a click event handler like here, call it on login, and when it is clicked, the event is catched by JavaScript. It is bubbled into our code because we registered an event handler there, and so our code is called from within JavaScript. And then, well, we just fetching some values, checking if the username and password matches, and if they do, well, we are throwing an event to a channel. So you might wonder, well, or you might say, well, I don't want to create a complete front end in the code behind using such a library or the plain syscall.js library. Well, I have good news for you. You don't have to create everything from scratch again. There is a framework called Vugu. And also good news, Vugu also supports TinyGo. So Vugu has React, Vue, whatever like-ish syntax and way of creating front ends. So if you have some experience with Vue, Angular, or React, and you want to create front ends in WebAssembly using Go, you might want to have a look at it, as it supports TinyGo. But it is still very experimental, and also the TinyGo support is still in a pretty early stage. So don't expect too much of it right now. So more or less, you should, if you are more or less now interested, and if you all other following great speakers after me are finished, you might want to get to know more about TinyGo. So don't forget to follow TinyGo on Twitter. Join the TinyGo channel on the Gopher Slack. Follow La Pipa TV on Twitch, which is Ron Evans, who is also here with us today. And well, plainly just visit the website of TinyGo. And keep in mind or note, I have encountered the TinyGo community to be extremely, and I really mean extremely helpful and nice to each other. So I had really lots of dumb questions over the time. And I got a question and a really good answer to, I guess, all of my questions. So don't be afraid to ask. No one is biting in there. Maybe I'm biting, but that doesn't count. So just join the community, get in touch, and start working with TinyGo. So, and now is the time, you're more or less coming to an end, to do some advertisement for myself. So I wrote a book about TinyGo. It's called Creative DIY Microcontroller Projects with TinyGo and WebAssembly. And you can learn how to set up TinyGo and your IDE. You learn the basics of microcontroller development. You learn what GPIO, SPI, I2C, and so on is, and how it works and how to use it. You learn how to write your own drivers. And you are also going to create WASM apps and microcontroller, which sends data over Wi-Fi and so on. And you can get it basically at every bookstore out there. Here's just a link to my repositories. I'm going to share the slides at the end of the day today. So if you need any of these links, don't be afraid. I'm going to share this stuff, and then you can find the links. And also, yeah, a big thanks to test.mosquito.org for for providing a free MQTT broker in the web I'm often using when testing out stuff. So really nice from these guys. And more or less, I'm already done.
Awesome. Well, thank you very much. I think on the topic of your book, I know that we have some giveaway copies that we that we have available to give away. I don't know whether you wanted to intro that or whether you wanted me to.
Well, you can do if you want to, so I'd appreciate it. I'm not the best. I'm not the best in advertising things, so I let you do it.
No, for sure. Okay, awesome. So Tobias's book, awesome. He is giving away 13 copies where you'll get a 20% discount to 13 people who answer a question to make sure that you were listening to the talk very, very closely. And I think Wilken has our question. I don't know whether I can get him up. Wilken?
I'm sorry, I was doubly muted.
Okay.
Technology. No, so I think I got the question from the talk, but Tobias definitely let me know if I misstated it. So the question, just to reiterate, so we're going to ask this question, and the first 13 people to respond to this question via email, you can send it to Wilken, Wilken at gobridge.org. That's GOBRIDGE.org. And then the first 13 people to get this question right, I will work with Tobias and teams to get you an ebook or a actual physical copy of the book. Okay, so what was the question that I wrote down? I think the question was, how many microbots does TinyGo currently support? Is that
microcontroller bots, yeah.
Microcontroller bots. There we go. I felt like there was controller in there, and I'm like, wait, but yes, microcontroller bots.
So now the question is, do we want to have the answer of the number I stated in the talk, or maybe the current answer from a repository with, I don't know.
No, so the answer was from what you stated in the talk. So where everything is based off your talk. So rephrase that question. How many microcontroller bots did Tobias say is currently supported by TinyGo? First 13 people to email that to Wilken at gobridge.org will win one of these lovely books, either an ebook or physical copy. All right. So that's that. So you'll be hearing from us after.
Get in there fast, because I've already emailed.
Yes.
I want that book. Awesome. Well, thank you so much, Tobias. Really, really appreciate your time. Obviously, for those watching, feel free to ping any of your follow-up questions in the Tiny Tech Go Slack channel or in the YouTube channel. We will be keeping an eye on that. And otherwise, obviously, feel free to, tweet at him, ping him directly on Go for Slack if you have any specific questions. He is a wonderful human being. So do see him as your guru for all things tiny tech.
Yeah. Angelica, if it's okay with you, before we switch over to the next speaker, we do have one question that came in for Tobias. And the question is, does TinyGo support for 8-bit microcontrollers? Does TinyGo have support for 8-bit microcontrollers? For example, the Mega 8535.
We generally have support for some 8-bit microcontrollers. Mega, what number? I'd have to look it up.
Oh, okay, so it was Mega 8535. So if you have to look it up, that's fine. And what I'll do is I'm going to thread this question in the Tech TinyGo channel, and then you could answer it there.
We can answer it. Okay.
Yeah.
But yeah, the general answers, we have support for 8-bit controllers, or if we have it for this specific one, I'll look it up and answer it.
All right. Well, thank you so much, Tobias. Really, again, thank you. Awesome talk. Really cool to learn about all this stuff. This is new to me. So thank you again for speaking and for sharing what you know with the community. So stick around for the rest of the talks if if you can.
So I'll do so. Thank you very much for having.
Sweet. All right. Cool. So Angelica, I think great stuff. We got, it seems like we have a little bit of an issue with the Slack, the Go for Slack sign up. So if you're trying to sign up for that, it might not work, but we're working on it. So hopefully we can get everyone squared away. For now, if you want to ping us or hit us up on, if you want to ping us or ask a question, please try to use the YouTube chat until we get that all squared away. Awesome. Okay, so I guess with that being said, I'm going to go right into the next talk, if that's okay. Yeah. Hello, David. I have the opportunity to introduce you and tell a little bit about your talk before you get talking. So David is a senior software engineer working on the Reader Revenue team in revenue technology. He has over 30 years of experience in software development in various industries and companies ranging from two-person shops to global Fortune 10 companies. He currently enjoys writing Python and Go, wrestling with gobs of data, working with microcontrollers, and unintentionally blowing them up. I'm very interested in hearing more about that. And torturing his daughter with really bad dad jokes. Oh, I feel you. I'm right there with you. Today, he'll be comparing TinyGo, Arduino, and MicroPython. Microcontrollers are getting smaller, more powerful, and are easy to work with. No longer are they in the domain of electrical engineers using dedicated programming hardware and C or assembly language, thus making them a little more accessible and being able to program them with languages either. And this is where enter TinyGo, a Go compiler for tiny places. So today, David is going to be answering some questions and figuring out how does it compare between Arduino, C++, and MicroPython, and how easy it is for a Go developer to get into the physical computing, and how to get into physical computing and actually use TinyGo. So with that being said, David, welcome. Thank you for joining us here today.
Thank you for having me. Let's see, where do I share my screen here? I don't see the screen sharing option.
It should be somewhere in the little on the toolbar, the little floating toolbar somewhere. I don't know. I feel like it always moves on me. So
let's see here. No. Share screen. It was right in front of me. Right. So let me know if you guys can see the screen. See my presentation?
Yep, all good. Floor is yours.
All right. So I'm gonna try a little bit to channel some Bill Kennedy energy here, but I know it might be impossible, but I'm gonna try. All right. So let's get going. So I think the introductions are already done, except for the part that I work at the New York Times. So I actually, before COVID times, I used to bump into Angelica in the hallway all the time. So what we're going to go over today, I'm just going to give you an overview of the project we're going to be working with to do the comparison, and then we're going to go through what the project looks like in Arduino, what it looks like in MicroPython, CircuitPython, and then TinyGo. And if we have time at the end, I'm going to go into a more detailed example to kind of show some really cool features of TinyGo, like being able to use Go routines for things that are kind of gnarly in Arduino. Okay. Just a little, I'm going to stand on my soapbox for a second here, just before we get going. I hear this all the time, like I build cloud solutions. Why should I care about microcontrollers? Well, one of the things is that, to invoke Bill Kennedy again, his concept of mechanical sympathies. I think working with microcontrollers, because you have to work within a very constrained environment, and you have to understand exactly how the machine works in order to get the best out of it. It really makes you a better developer. So, and also it's been known to, like, just being able to manifest something physical like that from your code, it gets the creative juices really going. So, and that kind of spread out to your entire life. So, microcontrollers, yeah. All right. What are we going to be doing? Well, seeing as we're all at home with COVID, and you every now and then you want a high five or a fist bump, and there's nobody around. So this is what we're going to do. I hope you guys saw that video. It's a silly little machine. It turns out to be quite simple. What we have here is an Adafruit Trinket M0, which is a 32-bit microcontroller running at 48 megahertz, has about 32K of RAM to deal with. It comes with CircuitPython already installed. It doesn't support MicroPython, but it comes with CircuitPython already installed. I'll get into what CircuitPython is a little bit later. But in addition to that, we have a micro servo motor, essentially, which is going to be moving our arm up and down. And we have right over here on the right, you see these two little circles are the this emitter and receiver for an ultrasonic motion sensor. And then, as you can see in my build over here, I put it together in a little case with a battery and everything, so I can get my high five going. All right. So this is the circuit that we're going to be putting together. Basically, it's like I said, the Adafruit Trinket M0 and the ultrasonic sensor. So very simple little project. Oh yeah, one thing I missed. In testing this, I did in order to do with MicroPython, I implemented this also on the WeMOS D1 Mini, which is an ESP8266 device, and I also ran this on an Arduino Nano IoT. Okay, so let's take a look at what this looks like with Arduino. So the code is pretty straightforward. You have, what you have here is you set up we import the libraries for the servo and the ultrasonic sensor. We set up some defines for things like what pins we're going to use for the trigger pin, the echo pin of the ultrasonic sensor, the positions of the hand in terms of degrees for the servo, and our reference to the built-in LED. We instantiate our devices, and Arduino code comes with is structured with two very important functions. One is a setup function, which runs only once when the device boots up. So you put things in there to initialize components or initialize variables and set things up. And the second part is the loop function, which the Arduino environment just calls over and over again. So it'll basically run the code, get to the bottom, and do it again, and do it again, and over and over and over again. So what's going to happen in that loop is that we're going to basically read the ultrasonic sensor to see how far away something is from the top. So if you look at the video here, if I put my finger, let me turn it back on again. If I put my hand a little bit above it, it slaps me. So that distance I defined as 40 centimeters, right? So if something is within 40 centimeters of the device, it will turn the LED on, wait for half a second, put the hand up. It tried to slap me over there. It's very angry. You'll put the hand up and then gently bring it back down again. Otherwise, you'll have some, I just want to make it a little bit more gentle going back down. And that's it. Turns the LED off and waits 50 milliseconds before it does it all again. All right, so that's what the code would look like in Arduino. Now, Arduino is a really cool environment because it was created by a bunch of engineering students in Italy to make things easier and cheaper for engineering students to be able to build these prototypes and so on. It spread really rapidly and provides a really open environment for tinkerers and hobbyists as well as professionals. Okay, let's take a look at what this would look like with MicroPython. Exact same situation. So MicroPython was created by Damien George, who's a theoretical physicist. And his focus really is to make this a rock-solid environment for industrial applications like robots and control systems and stuff. I believe some part of the Mars rover, the latest Mars rover, actually runs with Python or MicroPython. Okay, so how is this structured? Just like the C equivalent, we import some libraries and some modules. We set up some constants, and then we have we define a function called run. This is not necessary, but it's one of the optimizations that we do with Python, because anything that runs in the global space in Python runs a lot slower than things that are run in a local scope. So for instance, if I am referencing variables that are local to a function, that's a very direct lookup to access that variable. Whereas if the variable is defined in the global space of the program, it has to go first look in the local scope, then go look up that variable in a dictionary and so on in the global scope. So it adds some extra time to run everything in a function, and that's a little optimization for MicroPython. So the first part of the code here, basically, as I put the comment on here just to show the how it equates to the Arduino environment. So the first part equates to what you would normally put into like the setup routine in setup function in Arduino. It's one-time configuration setup code. Then since there's no loop function in MicroPython, and then the way it runs, you basically have to create an infinite loop essentially. So it's, while true is an infinite loop, and in that loop, you do whatever the action is that you want to your project to do. So in this case, just like the Arduino one, it reads the sensor and checks to see whether the sensor is within your sensor has detected something within the threshold. If so, turns the LED on, moves the hand up, and brings it back down. So as you can see, let's go back to the Arduino one. So we have 41 lines of code for Arduino, 34 lines of code for MicroPython. So far, Python, true to its nature, is really concise and small. What does it look like with CircuitPython, right? So CircuitPython was actually created by Adafruit and as a fork of MicroPython, because they wanted to kind of change the way it operates and how it interacts with the user, because their focus is more beginners and education, right? So they wanted to make it so that you don't have to flash CircuitPython onto a board. Your board comes with it already installed. You don't have to figure out how to connect through some sort of serial mechanism to copy up code from your machine to the board, because CircuitPython devices expose the code as a USB drive, essentially. So you just basically drag and drop or edit code directly on the board, which is pretty cool. But one thing that you'll notice right away is that the approach that Adafruit decided to take with CircuitPython makes it a little bit more wordy. So you end up with longer code and more code to do the same thing. So for instance, with CircuitPython, I can set up my LED or whatever device I'm using with one line of code. LED equals pin, what pin I want to use, and to direct the type of interaction with that pin. So that pin is an output pin in this case. With CircuitPython, you must first declare your LED pin, LED device, and then set the direction with a separate call. So it's a little more wordy, but I guess for teaching purposes, it's more clear as to what's happening inside of the device. All right. So now this brings us to the TinyGo. I hope that you can actually see that code there. I'm actually going to jump into an editor to show the code and some examples later. But I just wanted to show the code on here for the comparison. So, like Tobias went through, TinyGo is what it is. It's really tiny. I mean, in terms of what it produces, it's really cool. It uses LLVM as on the back end to do all that compilation and optimization of the code to generate those tiny binaries. And I think the coolest thing is that it's just standard Go, right? So aside from libraries that are specifically created to interact with hardware devices and so on, the language is just Go, which is really cool. So you get access to probably most of the standard library, the things that make sense. Like you don't need some of the more complicated parts of the standard library on a tiny microcontroller device, right? So those things may not be pertinent, but you still have access to that standard library. You get the readability of Go, you get the concurrency features of Go. And ever since it was officially supported by Google at the beginning of 2020, it's been moving really fast. So as an example, when I first started looking at TinyGo and this particular type of project, I found an example of how to use pulse width modulation, but it was only for the Arduino Uno. That code didn't work on any other microcontroller because of various reasons. And I was kind of upset about that, but then what I didn't realize at the time was that in the background, the TinyGo community was actually making changes to how all this stuff works and simplifying it and trying to make it more common across microcontrollers. So what you see here in this code is the majority of the result of that work. I think that they still have some work that they're completing, but so it's still in flux, but the results are pretty good. So what we see here is we set up our variables. We set up our pulse width modulation pin. Actually, the internal timer that's being used with the pulse width modulation. We set up the pins that we're going to use for our ultrasonic sensor and LED and so on, and servo. Actually, we don't need to set up the servo here, it's down below. And we set up our positions for the hand and so on. Down here, we instantiate our sensor on line 27. We configure it. We make sure that the LED is configured as an output pin. And just for comparison, to configure a pin for output, let's say, on TinyGo, it's the pin variable .configure machine.pinconfig mode pinconfig pin output. Right? So it's a little wordy compared to MicroPython, which is really succinct. And in Arduino, it's basically just saying pin mode LED and whether you want it input or output. But it gets the job done. And I see the method to the madness, I think, because when you have more complicated pin configurations, you can put it all together in that structure and it becomes more readable and understandable. Okay, so after all the setup portion, which runs once, just like MicroPython or CircuitPython, you need to set up your infinite loop. So in Go, this is the empty for clause. So basically, this is just going over and over again. And what it's simply doing is, again, reading the ultrasonic sensor. If there's an object within range, it turns on the LED, raises the hand, brings it back down, turns off the LED. So yeah, that's what the languages look like. Let's see, how much time do we have left? I'm gonna kind of just switch over to okay, so I hope you guys can see this, my editor. So I'm going to go, we already went through the high five machine. I'm going to look at the another example. So basically a temperature sensor, a BME 280 temperature sensor, and it's going to display the results on just a tiny LED display. Let me just show an example of what that looks like here. So, oops, this is basically what the output would look like. So it's pretty cool. So this is a bit more involved. The things that we all want to call out. Actually, wait, what? Am I looking at the wrong thing here? Yeah, I'm still looking at the high five. Let me close this all up. Okay, there we go. So in this example, to compete with Go-routines, I'm going to actually use a library called Task Scheduler. And it's a C++ library for Arduino. And what that basically does is you set up functions for the things you want to run in the background. You instantiate tasks for those that call those functions after certain periods of time. So in this case here, for the sensor, I'm going to call that function every 500 milliseconds, and for the button, the task that listens for the button presses, I'm going to call that every 50 milliseconds. Sorry. This is the function that sets up the that reads the sensor and calculates the temperature. The sensor returns the temperature in Celsius, so it needs to be converted to freedom units. And then we display the readings.
Sorry, excuse me, David. I always see as a white screen.
Oh,
I don't know if you, yeah.
Okay. Let me reshare.
Right. Thanks.
Where did it go? Do you see
Yep, all good now.
Okay, sorry.
Thank you. Oh, no problems. It happens. Thank you so much.
So okay, let's go over this again. So we start with the task scheduler library that we import, and again that basically sets up a method of doing asynchronous or concurrent calls in Arduino. So we set up our two functions, one for reading the sensor and displaying the data, and one for listening to the button. And the button press signals to switch the display between Fahrenheit and Celsius. Here we set up the two functions to be called by the task engine. One every 500 milliseconds, the other every 50 milliseconds. And here we see the actual code to read the sensor and display, blah, blah, blah. Nice thing about the Arduino libraries is that we have lots of fonts fonts available to use with the displays. And TinyGo actually has this also, which is pretty cool. I'm not actually going to go through all this code, but basically, okay, so here's the button handler that just Listens for a button press. If it was pressed, it does some debounce, and it switches a flag, the show Celsius flag. And based on that, the display routine would display either Celsius or Fahrenheit, depending on the state of that flag. All right, so this is the Arduino code. How would this look like in Python? Well, very similar. I mean, you have routine, you have modules for the OLED display. You have modules for the DMA280 sensor. This is the code that deals with fonts. The issue I've had with doing this in Python is that all this code, so the fonts, just like with Arduino or TinyGo, the fonts are basically code files with bitmaps of the fonts, right? So whatever font you want to use with Python would have to be on the device. So if your device has a limited amount of storage space, you kind of limited in what you can actually deploy to that device. So in this case here, I'm stuck with one font. With MicroPython, the garbage collector is kind of optional, so you can kick it off by calling gc.collect. Here I set up my devices, display. Nothing really impressive here except that it's just a longer piece of code, right? Let's go to the Go version of this. You have, just like Arduino and MicroPython, you have drivers for the devices you want to use. And just like Tobias said in the previous talk, there are a lot of devices already supported, but more are being put on there as things progress and TinyGo matures. Tiny font, I'm really impressed with it. It's really cool. I think this was created by Ron, if I'm not mistaken. But I'm going to be, because of this, I think I'm going to switch to using TinyGo for a lot of stuff that I was using displays with. It's really cool. Okay, so we set up standard stuff we've seen before. We set things up in our variables. Okay, here's an interesting way I structured this code here. So just to mimic what Arduino does, I created a setup function and a loop function, and in our main, I just simply call one after the other. And setup does the setupy things, but at the end, I kick off my Go routine to listen for button presses. And then the loop function, just simply all it's doing is reading temperature, display, read the temperature, display, read the temperature, display. And whether it displays Celsius or Fahrenheit would depend on the flag set by the button handler. So as you see here in the button handler, what we're doing is if the button is pressed, which in this case here is just, you figure that out by calling get on the button, and I just set the LED to high here just to indicate to the user something's happening, and I flip the flag and debounce by just waiting for. I don't allow the user to make another selection within 500 milliseconds or half a second. Okay, and then down here you have the code for actually working the displays, putting text on there, formatting things, and so on. And at the end, it just calls display.display to actually correct the content to the OLED display. So that is what I wanted to show there. Let me go back to my presentation. Let me just, where am I? Okay, so just to wrap it up, I have the sample code that that shows there's 3 projects in there. Just the basic Blink in both in Arduino, MicroPython, CircuitPython, and Go, so we can look at what they look like, how the code is structured in all 3. Same thing for the High 5 project. And then the last project with the BME2A temperature and humidity sensor and the OLED display. So if you go to this this repository, you will see that code. Also, I put some references on here from the Arduino website, MicroPython, TinyGo, and I highly recommend Tobias's book. I went through it cover to cover and learned a hell of a lot. Excellent book. And with that, I thank you. And that's all I have.
Awesome, awesome. Thank you, David. I'm going to go ahead and unpin you. Great talk. Can you hear me? Let's see.
Yep.
Yeah. All right, go back to standard view. Awesome. Yes. Thank you so much. We have some questions, and I also want to say thank you to Vanessa, who's already within Gopher Slack answering them as well, but I did want to bubble them up and get your thoughts on this for our folks listening over on YouTube who may not have access to Slack at the moment. First question that came in, is there an issue when it comes to speed and performance if we write it in Python rather than C or C++?
If you're writing very timing sensitive stuff, then yes. Like if you're going to be doing encryption or something like that, Python will definitely be will have issues. But there's a great talk by Damien George that's out there on YouTube that shows various optimization techniques. So he showed taking a piece of code in Go, and basically all he was doing is how fast the code can actually blink an LED. And he showed the basic Python, MicroPython code running, I think it was over 20-something megahertz, 27 hertz. I forget the exact speed, but basically there's only so fast that it can run. He made some simple tweaks with using a local variable versus a global variable, and I forgot what the other approaches he took. Just very simple stuff, and it doubled the speed. And at the end of it, he was able to, just by using simple, well, not simple, but things. Some of this stuff makes the code not as readable, but using still pure MicroPython, he got it up to a couple hundred times faster than how it'll run regularly. Then he showed an example of putting inline assembly in the Python, and that got it up to, from like 50 hertz to 27,000, which is a huge, boost. So, and the other approach that I saw from another talk was to take your timing sensitive stuff, write it in C, and then call it from Python. So you still have that productivity that you get from working in Python, but then you can get really good performance with your timing sensitive stuff.
Awesome, good stuff. So I guess go a little low level language for the time sensitive stuff, and then just interface with it on the Python side. Super dope. Great to hear. We have another question on there, but I don't know, Angelica, are we good for one more question, or maybe you can?
Yeah, we're good for one more question.
One more question. Awesome, David. The second question, and it seems like you kind of alluded to this already, but which of the programming languages, TinyGo, MicroPython, or C, C++, is most often used in professional applications?
I would say for professional applications, I know the Arduino company is getting into, they have a new professional line of devices and consulting services and stuff like that. I know that Arduino has been used in commercial stuff, but MicroPython has been used in industrial stuff since almost the beginning. I mean, there was a traffic control system in Germany that was written in MicroPython. So basically, it counts the number of cars that pass by going over the sensor, essentially. And I think there's something on the Mars rover that's using MicroPython. But I think these guys have, they're gonna have to, TinyGo is coming for them. Because with TinyGo, not only do you get the performance, the performance is there, but not only do you get the readability and the productivity that you get with Python, but you get really tiny binaries that run really fast. As an example of the tiny binary, I compiled the hello, just a Blinky executable in TinyGo, 500 bytes. Actually, it was less than 500 bytes for the Arduino Uno. I mean, I just blew my mind. So I think you're gonna start seeing a lot more professional stuff being done in TinyGo.
So really, really good to hear. And I'm sure all the speakers here really would agree with you and are very excited to hear that news, about TinyGo eating up the space. So again, David, really thank you so much for being here with us. I'm going to hand it over to Jessica to Jessica, I apologize, to Angelica. Sorry, looking at too many screens here. Angelica, in case you have anything else to say before we introduce our next speaker.
No, Angelica, that's what I'd like to say. No, I just want to thank David. He is a very dear colleague who is a wonderful human being, so clever, so talented, but also so willing to teach and help people who are not as familiar. So I would really encourage you, tweet him, email him, reach out to me if you have any trouble finding him on social. He's a wonderful teacher. He's taught me a lot in this space. So I would really encourage anyone who has questions, don't hesitate, reach out. And from one wonderful gopher on to the next, who is also a wonderful teacher and a really valuable asset to our Go community. So I have the pleasure of introducing Vladimir Vivian, who is a software engineer and a technologist who enjoys contributing to open source and working with Go, of course. He's the author of a book titled Learning Go Programming, and he currently works at VMware on cloud native related technologies such as Kubernetes. And today he's going to be talking about real-time video capture with Go, using the Video for Linux API, so V4L2, directly to do real-time video capture for attached camera hardware devices. So without further ado, welcome. Very excited, Vladimir. I will pass it over to you.
Awesome. Thank you. Thank you. Thank you for the introduction. And as Angelica said, my name is Vladimir Vivian. Let me go ahead and start my screen share so we can get going. There you go. I want to share the whole desktop. Okay, so I don't have a backup screen, so hopefully you guys can see my screen. And let's go ahead and get started. All right, so as Angelica said, my name is Vladimir Vivian, and today we're going to talk about real-time video capture with Go. So it's a bit of departure from what the previous two speakers were discussing, which is TinyGo. And truth be told, when I was approached to do this presentation, I thought about doing something in TinyGo, but I did not have everything I needed to get going with TinyGo because I wanted to do a specific presentation. But I had a problem lingering, so I went ahead and worked on that, and today that's what we're going to talk about. once again, I've already had my introduction, but I am Vladimir Vivian. I'm a software engineer. I work at VMware currently, but in the cloud native space. But I'm an all-around technologist. I enjoy working in technology, and the stuff we're going to talk about today has nothing to do with my day-to-day work, but it's interesting, and it was a great find. So I dove right in and started playing with it. Okay, so this is what we're going to talk about today. What is it that what's the motivation? What is it we're talking about? We're going to look at video for Linux a little bit. We're going to explore what video for Linux v4L2 is and how it works with Go. And then we're going to look at Go4VL, which is a little project I started to capture everything that I've learned during this exercise. And then we're going to look at a bunch of demos. So I'm going to move fast so I can get to the demos, because we have a lot of code to look at, and then the demos. All right, so right off the bat, everything that I'm going to talk about, everything I'm going to discuss, all the source code, all the examples, I have on GitHub. This is the GitHub repository. If you wanted to turn off everything and walk away from the presentation, don't do that. Know that everything I'm going to discuss and talk about is there. And then early this morning, I released this blog post on Medium that pretty much captures everything I'm going to talk about today. So again, it's there for your, these are resources if you want to check them out. All right, so what's the motivation behind this, right? And just like anything else and everything else for most of us in the last couple of years, it had to do with COVID. So basically, I wanted to build a webcam because at one point, if y'all remember, there was no way, it was hard to find a camera, a webcam. And I wanted to find something, but eventually that turned into a hobby. I just wanted to see if it's something that that I can actually build, and started to dig around and see what's available. Eventually, I came up on a lot of documentation, a lot of information, but it was a lot. First I had to learn about Linux device drivers. Then I had to figure out what USB video classes are, because there are such a thing. And then USB video class gadgets and how to set them up. Video for Linux API, which is what we're talking about today, and lots and lots and lots of C. So finally, when I realized that it would have been too much for me to learn all this and build something, I was like, okay, for now, what I want to do is figure out how to capture video using the Video for Linux API. And truth be told, throughout the year last year, folks have figured out how to do exactly what I wanted to do with this is it right here. I don't know if you can see it because I don't have, like I said, I don't have a screen. This is the camera. This is the Raspberry Pi Zero, okay, with the HQ camera, with the HQ lens attached to it. But anyway, like I was saying, folks around the web have figured out how to do what I wanted to do, but they figure out how to do it with C. And naturally, as somebody who write a lot of Go, I'm like, hey, can this be done with Go? So before I answer that, let's obviously the answer is yes, but before we get into it, let's see what Video for Linux is all about. So what is Video for Linux, or V4L2, which is the second iteration of Video for Linux? Well, it's part of a large corpus of code that's part of the kernel that has to do with media infrastructure. You can use it for to capture video or to output video, device control, device capabilities, pixel format configuration, because if you're going to capture video or images, you have to tell the device what is it you want to capture and what format, if the device supports it, that you want to use, and a whole lot more that we're definitely not going to cover today because it is, like I said, it's a large API. But today, what we're going to focus on, as I said earlier, is video capture and whether or not we can do it with Go. So now let's see what Go and Video for Linux look like. So how does Go work with Video for Linux? Well, you have, a couple of options, right? So we know that from Go, you can make CGO, you can use CGO to make calls to a C library and use what's already available. I could have gone that route, right? But also in my research, when I was looking into this, what I found out is everything that's required to make Video for Linux work are system calls. Well, it turns out that Go has those system calls built in. So what are those system calls? Well, you have open and close, which we do that, all the time if you've ever created or opened a file in Go. But we also need a specific system call that is that Video for Linux relies on a lot, which is IO control, and we'll take a look at that. Map and unmap. Now, these two system calls I had never used before, but luckily they are well supported in Go, and they allow you to basically, what they'll allow us to do is map a buffer, a local buffer to our program actually, it's the reverse. We're going to map the device's memory into our running program. That's what memory map does, mmap. And then unmap releases that memory. And then select, which is another system call we're going to see. And basically, we're going to use select to so that we can be notified when our device is ready, so we can read the data that we want. Okay. Now, everything else, so beside those system calls, everything else you have to do yourself, right? Including the values, the data types, and functions that you need to talk to the Video for Linux and to make it work properly. Because we're not gonna use an existing C binding or a binding against an existing C library to do it for us, we have the responsibility of creating all the types and everything else that we need so that we can talk to the Video for Linux library. Luckily, if you've done Go or if you've dabbled with CGO, you know that most Go types map really well to their C counterparts, which is what Video for Linux supports. So once we figure out what we need to and how to map our types, then we can use them and make calls to Video for Linux. Okay. So now here's an example of what I'm talking about. At the top, we see a Go type called request buffers, and we'll see that being used in a minute. And down in the bottom, we see its counterpart in C. And as you can see, besides just the name difference in the types, we can pretty much see how well the Go type and the C type maps, how they map onto each other. All right, so I've blown through really fast about Video for Linux. So now let's do an actual walkthrough. Again, the code that we're going to look at is available on GitHub. So you don't have to pay too close of attention, but if you want to go back and check it out, you're welcome to. Okay, so let me, oops. Yes, we can do better. Let me go to my editor. So hopefully you can see my my VS Code screen. Okay, so now what we're gonna do, just to prove the point that this is doable and it can be done, I'm gonna walk you through how to use Video for Linux directly from Go and everything that I need to make it work, I'm going to declare it in this one file. As you can see, looking at the import section of this source code, there's not a whole lot of dependency outside of the sys Unix package. That's the only thing external that we're going to use. Everything else, we're just going to declare ourselves and use it to make it work. Now, every portion in the code, I try to give you a link if you want to go back and look at what the C counterpart looks like. So I put a link there so you can go back and check it out. And the same thing, I've done the same thing in the in the blog post. As you read the blog post, I put links in the code so you can click and go see what the C or whatever we were using, where it comes from. Okay, so let's go back to the code. The first thing we're gonna do is we're gonna declare a layout of our commands that we're gonna send to the Video for Linux API using IOCTL, or the IO control command. Okay, so that's what we're doing here. Again, if it doesn't make sense, that's okay, but know that, you know, I'm not making any of this stuff up. This is values that we need so that we can craft our commands to the Video for Linux API. So this whole block basically describes how we want to craft our commands, the size. So each command to the IOCTL is a 32-bit value, and different portion in that 32-bit value means different things. So that's what we're doing here. We're laying out that command so we can use it over and over in the rest of this code. All right. And again, if you want to figure out, or if you want to see where that comes from, here's a link right here. You can click on it and it'll take you there. All right. Now, the first thing we're going to do is define a function that takes that layout, and when we give it a set of parameters, it'll come up with a value that Video for Linux understand. So IO enc, or the IO encoding, it does that for us. Again, if you want to know where that comes from, click on that link above. All right, next, we do some wrappers for the IO encoding. One is for when we want to send functions that is just read-only. If we send a function, if we make a system call to Video for Linux and we know that it's just going to read only, we're going to send it like this. So these are a convenience function that uses that function for us. And then we have IO encoding just W, which is, again, that's the reverse. So if we do a function call to IOCTL and we expect a value to be written back to us, then we're going to use this. But if we want both read and write, meaning that we send a value to the API or to the device driver, but we also expect the device driver to return back something to us, then that function call will require a read and write. So again, this is a convenience function that calls the IO encoding for us. This 4-character function, we use that in one place, and we use it to encode or to tell the API that we're interested in using when we're setting up our pixel format. We're going to use that function to tell us the Video for Linux API which pixel format we're interested in using, and we'll see that in a minute. Okay, and then here we have the IOCTL. And IOCTL is IO control. It's well known and well defined in the C world. Here we're basically wrapping a system call that does the IO control for us. And this is using the external package, the sys Unix package to do that call for us. So as I said earlier, we're going to use the 4 character encoding to create a value so that we can tell the Video for Linux API which format we want to use. In this instance, we want to use the MJPEG format for our video. All right. Like I said, you saw the you saw the slide earlier. You do have to declare everything because we're not relying on an external package written in C. We're doing everything ourselves. So there's a lot of groundwork we have to cover before we can send our first command. So that's what we're going through. More values that we need, field any, field none. We're going to use that a little bit later. Another set of values we're going to need is to tell what type of functionality we want to use. When we're using the IOCTL command. Here we want to tell the driver that we're interested in doing video capture. We're not doing video output, nor are we doing video overlay. I can actually delete these 2 lines and my code will still work. All right. Now, the first type that I need is called format, and we're going to use it to send, to tell the IOCTL, to tell Video for Linux API what format we want to use. Now, it takes 2 types. One is called format. And again, I give you all the links here. If you want to go to see, if you want to go in the C code to see what it looks like. Matter of fact, let's do this. Hopefully I'm not breaking anything. There you go. This is, let's make this a little bigger. Yeah. Did I lose it? Yeah, it's too big and I lost it. Hang on 1 second. There you go. So this is the C format equivalent of what I'm doing in the Go code, right? So we have format and we have pixel format, which map to V4L2 pix format. And these 2 types I'm going to use to set the format that I want my driver to be in once before I start capturing data. And we do that with this function. So I'm going to I declare this function to do that for me. And later on, I should say, down in the code, we'll see how we use all of these functions as we talk about them. So we're going to set the format. We pass it pix format. And now you get to see an actual IOCTL call being made. I'm doing some unsafe pointer magic here. And the only reason why I'm doing that is because if you look at this type right here, there's an embedded union, an embedded C union, union type in this C in the structure. And I'm not going to go into the detail why this works, but I had to go and research how to do embedded union with Go, but it does work given that I tell it that this type has, I give it basically, actually, let me go back here. You see this data type is 200 bytes. It is the largest type in this embedded struct. So just by doing that here, I tell, I'm going to tell Go that about the largest member in that struct. And just doing that, Go will automatically figure out how to bring in that embedded union type and cast it to the proper type, which in this case, it is the pix format, which represents the embedded union type. Anyway, that's all I'm going to say about that. If you're interested, do a search on Go and embedded union. You'll find more of your fair share of information. Okay, now here I'm calling my the functions that we saw earlier, and we're setting up a value, and that value is the actual command that we're going to send to the via IOCTL. We're going to send to the Video for Linux to basically set the format for us. And this is the IOCTL call. This is the file descriptor after we've opened our files, and we'll see that in a minute. And this is the command. So this, all of the previous functions that we defined is building a value, a 32-bit and value for us that tells IOCTL what function or what command that we want to do. And then all of these are basically, the rest of this is basically the parameter to this command. So this command I'm sending to set the pixel format. Let's see, yes, and so we have to tell it how big the struct is so it knows how to read the data. And then if we're gonna receive data back, IOCTL is gonna use that information Video for Linux API was gonna use that information to return data back for us. All right, so that was a lot of detail, and the rest of this is pretty much the same thing. So I'm going to go a little faster so we can get to the punchline later. So more types that I need to define, and this one is to tell Video for Linux the different. It's to tell Video for Linux the different type of memory streaming that I want to use when I want to get the information from the device driver. For our use case, we're going to use memory map. And as I mentioned before, memory map allows our application to basically map into the device's memory space directly without doing any kind of memory copying back and forth. So we'll see further down how to do that. And once we have access to that memory mapped area, we can just read that data as if it is part of the application. All right, so here's the next type that we're gonna define: request buffers. This is the type we saw earlier, and this is the function that we're gonna use it with. And request buffer basically asks Video for Linux to set up to allocate buffers for us. All right, so we're gonna move on to the next one, buffer info. This is the next type we define. Again, all of this is coming from C. If you want to see what the original C type looks like, you can click on the link and see what it is. So I'm not going to spend too much time on that. So we have two more types: buffer info, buffer service. Excuse me. Buffer service is the type. Again, here we have another embedded union. So buffer service represent that type. We're going to use it to get information later. And then time code is another type that is, where is it? That we're going to need when we're building our our function call to Video for Linux. Now, the next function we're going to define is map buffer. And again, I've already mentioned that what map buffer does. So first, we're going to make a call to the to tell the Video for Linux that we're interested in setting up our buffer. So we're going to ask it we're going to query a buffer. So query buffer basically asks it asks the driver to not only, so earlier we allocated the buffer, but basically now we're going to query the buffer to get those buffers ready for us. And once that's done, we're going to get so we make our IOCTL call here. And when it comes back, the buff type that we pass to the IOCTL will have data that we actually need. So since we ask the driver to get buffers ready for us, it's going to come back with some information, and we're going to use that information to call the mmap so that we can properly set up our memory mapping. And once we do that, we're going to get a buffer that we can use locally in our application to read the data as the video comes up. All right. Now, start streaming does exactly what it does. It tells the driver to get ready to start streaming. Query buffer. Yes, I warn you guys, this was going to be a lot because, you know, we're basically, this whole demonstration is to show you all the steps that are involved if you were to do this yourself, and if you were to try to do it all the time. This is what you would need to do. So queue buffer, once our buffers are, once the device gets our buffers ready, we're going to queue it so that later on we can read that. So that's the call to do that. So I'm not going to go into detail. And then we have a dequeue buffer. When the device filled our buffer with data, we're going to use dequeue buffer to let the device know that we're ready to read that data, so that the data can be, so that the driver can go into a mode where we can read that data. So that's what dequeue buffer does. And you can see it's basically the same type of thing. We set up a type, and we use IOCTL to send that command to the driver. And then stop streaming does the opposite of start streaming. We tell the driver, hey, we're done. Go ahead and release your resources. Now, this function is interesting because it doesn't do any IOCTL command directly, or any video for Linux command directly. But what we're going to use it for is to monitor the device, so that when the device get into a read mode, meaning that we can go ahead and read the device, we'll use that as a signaling mechanism, so that we can go ahead and read the data from our mapped memory. And that's all this is doing. So this whole thing is doing that for us. All right, finally, we're into main. Hopefully, you're still with me. You haven't left the channel, the stream. Okay, so here's where we're using all of this. First, we open the device. Okay, we're just doing an open file. Next, we do a set format. So we saw that that function defined earlier, and we're using the pix format type to do that. I'm going to use 640 by 480 width and height. And then the pixel format is the MPEG. You saw that value earlier. That's what we want to use. And then field any, we're going to set that to field. Field, we're going to set that to field none. Okay, first thing we're going to do is do the request buffer, which will allocate those buffers for us. I'm going to do 3 just to have enough time, because this example, basically, I'm using it as a photo snapping example. So I want to make sure I have enough buffers captured by the time I even look up. So I'm doing 3, but I could have done more. I could have done less. Okay. I'm going to map the last buffer. Okay. So we're doing 3, 0, 1, 2. So the last buffer is the buffer I want to map. And that's the data I'm going to get back as a slice of bytes. Okay. Now we're ready to queue our buffer, and we're going to tell the device to go ahead and get our buffer ready for us. Start streaming. So after that point, the device is going to fill up our buffer, and then we're going to tell the device, okay, wait for you to go into in read mode, so I can now read that data. So we wait for it. Once we get past that point, that means the device is ready to be read. Now we dequeue that buffer that we had asked the device to queue for us. And at that point, we can go ahead and read the buffer, the mapped buffer that we set up earlier, to grab data from it. So what we're going to do is read that buffer, that slice of bytes, and we're going to copy that slice of bytes into a file. And that's exactly what we're doing in this portion of the code. We create a file called capture.jpg, and we just use regular Go code, regular file operation to write that data. And then after that, we stop streaming. So it's a lot. Let me tell you, I was confused for weeks researching how to use video for Linux, but eventually, yeah, it kind of made sense once I've read tons and tons of blog posts. Anyway, So this is where we are. Let's see if we can make that, if we can make it work. So I'm gonna go, hopefully you're seeing my terminal. I am logged into, so just so you can see what I have a Raspberry Pi, and then that Raspberry Pi is attached to a camera that's sitting above my monitor. It's basically a webcam. Okay, so now I can use the code that I just showed you to go ahead and trigger that camera, turn it on, and capture one frame. And we'll see what that looks like. Okay, so let's get out of this. All right, so it's already, again, I'm logged into the Raspberry Pi, but I have Go installed on Raspberry Pi just in case I want to build something. So I've already built the raw v4l2. So I'm going to go ahead and run the program. All right, so let's run that, and then let me get ready to smile, and then we're gonna grab one frame, like I said. All right, so that frame got grabbed. So let's see. Okay, now we see we have a new file called capture.jpg. So let me go into VNC right now and see if we can see it. Okay, right here. Did it work? Yay, it worked. So I was able to grab one, frame. Okay, big deal, right? Now, if this was the whole presentation, I would have been disappointed, but I took it a little bit further, and let's go back to this so we can, all right. Let me go back to the presentation real quick. Hopefully you can still see. Can we do better? Yes, we can do better. And through me looking into doing, preparing for this presentation for about a month on the weekends, I started with this project called Go for VL, or Go for Video on Linux. And basically the idea here is to hide all of this that we just talked about, and hide it away from you, and instead expose idiomatic Go types like channels, so you can just ask for a channel and consume the video or whatever you're doing. So now let's look at what that looks like. So we're going to look at two demos. One is capturing multiple images using that, using the project I just showed you. And then the other one is a live webcam that's we're gonna run on the Raspberry Pi, that's gonna stream me as we're talking and push that onto a web browser. All right, let's go back to the code. Okay, so where am I? There we go. So let's do capture. Let's look at this code. Let's use, actually, before I look at this code, let's look at what the v4l2 package does for us, and then we'll come back to the code. So v4l2, I'm not going to go through the whole thing, but I just wanted to show you that everything we were just looking, when we looked at the raw capture, because the raw capture example, I wanted you to see all of the steps that are involved in getting this thing to work. But this package hides all of that for you, but it does basically the same thing. We have a device type here, and from that device type, you can get pixel format. You can ask, you can open a device here. Actually, let's see, open a device. Okay, we'll get to the questions later. You can open a device. You can get device capability, crop capability, get pixel format. We saw that earlier. Set pixel format. Start the stream. What else we can do? We can do a capture, and with a capture, which we'll use in a few minutes, you can pass it a frame per second to kind of help you out with, so you don't, you can throttle and control how many frames you get in a second. We're not going to go through the code in detail. And then stop stream. But, everything that we did earlier in the raw example, all of it's basically the same thing, but it's being hidden from you, and it's captured here. For instance, you could see if I go to the streaming.go, you can see all of the gory detail of what's going on in the back end, all the types, and you probably saw the types, some of the types we saw earlier, but they're declared here, and everything that you need to start to stream is there for you. And again, the magic of abstraction, right? And computing. So everything that you need is abstracted away for you. So all you have to do is come to the use the device type, and the device type ultimately will give you a channel. Let me go back and show it to you right here. When you call capture, you get a channel of bytes, and those bytes are coming from the mapped area of the device, as we saw earlier. All right, so now let's go back and see how we can use this. Okay. All right, let's close this, and let's look at this example, the capture example. All right, capture example. This example is basically the same example as we did before, but instead of just one frame, it captures, I think, 10. Okay, so if we go down here and we look there, now, instead of doing everything that we did before, setting up the types, etc., we're going to use this package that we just looked at earlier. And here we do v4l2.open. It gives us a device. Once we have that device, now we can call set pixel. We pass it the pixel format that we're interested in. Now all we have to do is say start the stream, and I want to buffer 10 frames. So we're going to ask the device driver to talk to the device and allocate 10 frames for us, so we can fill 10 frames at a time. Now, once we have that, I can say I want to start capturing. When we call capture, we pass it a context in case we want to cancel that context before it's time, but we also pass it a frame per second. So here I'm only doing 15 frames per second. Okay. And I'm only laughing because earlier when I was looking at I was playing with this, I'm like, man, it looks a little choppier than, there's a little lag, but I was messing with it and set it to 15 instead of 30. And now it makes sense why my video was a little laggy. But anyway, so once we have that, we grab the 10 frames and we're going to loop 10. Actually, what we're going to do is loop 10 times and then stop everything, because this is the frame channel that we're going to get. Once we get the frame channel, we can loop through it, grab 10 frames up to total frames, and then we're done. As we grab each frame, we write that frame to a file called that with the prefix capture underscore JPG and the extension JPG. And for each frame, we write it to the local file system. And then once we're done, we call cancel to make sure we want to cancel the capture sequence, and then we stop the stream. Okay, so let's look at this real quick. See what we get. All right, so I already built it, so we can do capture. So now I'm gonna sit up. It's gonna take a little longer than before because we capture in 10 frames. So I probably have time to wave. Let's see. Yes. Okay. Now we should have captured 10 frames. If I do LSL, you see all these frames. we can look at these frames. I have VNC running still, so let's go back. And all right, so we see those frames here. Let's start with 0. Yeah, let's see. And we see if I step through, so basically I'm just stepping through by clicking the right arrow is just stepping through each frame for me automatically. So it's just, it looks like it's a video, but it's just each frame being shown successively. Okay, so that was that. Now, I took it a bit further. I was like, what else can I do? Well, it turns out I can build something else. Let's do the webcam thing. All right, so I took the, using everything that we just talked about and the API that I created, now I built something else, something that allows me to stream videos from basically that same setup, but push that those buffers to a web browser and create a webcam. So let's run it before we look at the code. So I'm gonna start it. All right, now let's go to my, hopefully you're seeing this. All right, let me reload. Okay, so you could see me. So you should be seeing me in the browser talking about the video, and I'm pointing and I'm moving. So everything that's going on right now is being captured via the Raspberry Pi and being pushed to my web browser. There you go. I made it a little bit bigger, and you can see it's, there's a little lag, but it's not too crazy. And you can, that's what I was saying earlier. You can adjust your frame per second to control that. And obviously, you should figure out what your webcam supports, because you don't want to overrun your buffers and you start, either it'll give up or you start getting even choppier result. Okay, so now let's go back to the code to see how this was done. All right, so now let me go back to the code again. So let's look at, and the other thing I wanted to show before I look at the code, if we go back here, as this is being streamed, you could see that I'm running an old Raspberry Pi, by the way, because I kind of glanced over and I saw a question, what kind of Raspberry Pi I'm running. This is a Raspberry Pi 3, and it's, it's a few years old, and it's not the last 4. But if you look down here, you could see that the cores are really not being taxed. And you could see the memory is staying stable. So, and the streaming is still going on in the background, by the way. So I'm still streaming. You can see everything is going on, but if we go back, you see that, I'm not putting on any hard pressure on the Raspberry Pi doing this. So I just wanted to point that out. Okay, so now let's go back to the code so we can see how this was done. All right. Where is it? There we go, webcam. All right, so let's go over this really quick. This is the Go file. And let's start here first. So we have a logo. That's the logo you see on the page. But besides the Go code, I have an HTML page, and that is the page that's being served here. That's what you're looking at right here. Okay, so I wanted to point it out right away. All right, let's go back to the Go code. All this is let's go to the main so you can see. All this is basically a web server. It's a web server code that's using the Raspberry Pi to capture the image, and then as I capture each frame, I'm sending those frames down the browser. So let's look at how this is done really quickly. So again, I'm using the v4l2 package, opening a device, getting the device capability. We didn't go over that, but that's one of the things you can do to see if you can basically, if you can do what you're asking the device to do, in this case, we want the stream, because you may have a device attached and it doesn't support streaming. So you can ask for device capability and then test those capabilities. So let's see. Okay. So next I set the, actually in this instance, all I'm doing is output that capability to the screen. Actually, if you wanted to see, if you, when I started the program here, you can see right here that this is what I outputted with the device info. Okay. All right. So let's go back to the code. All right. So next we set the pixel format as we discussed earlier. Now I said I'm going to start my stream, so I'm going to allocate 15 buffers. Okay. And now that I have my 15 buffers, I'm gonna start my capturing at FPS. I set FPS up here at 30, but I only did it that up here so I can display it. And if you go back, you can see it says down here, it says go webcam at 30 FPS down at this area here. Okay, that's why I set it as a global. Okay, so going back, now that I have my device set up, oh, the other thing I want to point out, once I call capture, I get my channel. I'm going to set that channel to a global variable so that anytime, at any point, somebody do a HTTP request, they'll be able to tap into that frame, that channel, and then start streaming right away. Okay, that's why I made it global. Okay, I'm pretty sure that it's probably a better way of doing this, but right now that works. And this is the the first attempt. This is the first iteration of this code, and I was like, I actually did a dance once I got it working properly, but I won't do it today. But anyway. So now I set up two routes.
Excuse me, Vladimir. I apologize. Sorry to interrupt. And I really love this talk. It's amazing stuff, the dance. But we're running a little over, and I want to see if we can move into the next talk because
absolutely. Thank you.
So So if you can refer folks to GitHub for the rest of the code. This is great. I mean, maybe we can set up another session afterward. I really want to see this dance and this 15 frame capture, but maybe we can. No,
actually, that was it. That was it. So I was just going over the code that does this. So that's it. And thank you for thank you for your time.
Yeah. Well, thanks for joining us today. Awesome talk. We got lots of good chatter in Gopher Slack and also on the YouTube channel. We've pinned all the questions there, so feel free to chime in, and look forward to seeing more of this. So thank you. And I should probably turn on my video. There you go, so you can see me.
Yeah, thank you so much. Really appreciate it. And again, all those who are watching, we pinged the repo in both YouTube and in the Slack channel, but obviously do feel free to tweet Vladimir, and I'm sure he'd be more than happy to answer any questions you have there. Thank you so much, and hopefully we'll talk again soon. Great.
All right.
So I'm going to pass over to you, Wilken, for our last but certainly not least speaker.
Okay, well, awesome. Well, again, thank you so far to all of our speakers and to all of the attendees for sticking with us. This is going to be streamed afterwards, so thank you. And Ron, thank you for your patience. All right, I have the pleasure of introducing our next speaker, Ron Evans, aka Dead Program. He is an award-winning software developer and expert in robotics, IoT, and computer vision, who is very active in the free and open source community. As a technologist for hire at the Hybrid Group, he has helped many clients such as AT&T, Intel, and Northvolt solve some of the most difficult technical business problems. Without further ado, I'm going to hand it over directly to Ron, and I'm going to pin the title for his talk in the channel and go from there. Ron, the floor is yours. Thank you so much.
Thank you. Thank you very much. Hello, everybody. Before I get started, I just want to say thank you so much to Angelina and to Wilken for all the great work putting this together. And I want to say thank you to Tobias, to David, and to Vladimir for the fantastic presentations. Really great work. Make sure that you check them out if you didn't see them, because a lot of amazing demonstrations and cool stuff. Anyway, hello, I am Dead Program. I am here with GopherBot, which is my programmable robot plushie, entirely coded with TinyGo. And I am here at La Pipa in beautiful northern Spain, where I do my stream every week. Check it out at twitch.tv/lapipa.tv. So without further ado, this is Go Without Wires. I am Dead Program, technologist for hire, you know that, at the Hybrid Group, where we are all technologists for hire. Well, aren't we all technologists for hire, really? But yeah, but specifically. And clients, most interestingly, the company Northvolt, where we are helping this wonderful Swedish company create the future of energy. Check them out. So, but also a lot of open source projects that we've over the last years. GoBot, which was one of the first hardware control software written in the Go programming language. GoCV, which is a very popular wrapper around OpenCV in the Go language that's used in a bunch of cool projects, very active project. And of course, TinyGo, which you much about from some of our other speakers, a really amazing project that we're happy to participate in. But this is a talk about wireless networking. And of course, when we mean wireless, we mean this time it's personal. Yes, we're talking about wireless personal area networking. Of course, Bluetooth. I mean, what other wireless personal networks are there? Actually, there are a few, but Bluetooth is the most popular. And so earlier this year, we released Go Bluetooth, which is a package written in Go that is specifically to let you use this very powerful, most popular wireless standard ever created by sheer number of devices. On Linux, of course, you need Linux. I mean, Linux is very important. Mac OS for all the hipsters and people who are cool. Windows 10, we only have minimal support still, but there is some. It needs more work if you're a Windows person. And then, of course, bare metal, which is where we run on microcontrollers, such as the one built into GopherBot, using the Nordic Semiconductor soft device, which is not open source, but is a free license. So very cool software. So, but what's so good about Bluetooth anyway? I mean, why use Bluetooth as opposed to Zigbee or one of these other, wireless personal area networking standards? Well, first of all, low power use. We don't want to use our precious batteries to stay connected. Another is high speed. You can do video, you can do audio, you can do lots of other things over Bluetooth. And then most importantly, it is already everywhere. I mean, don't you want to program for hardware that everyone already has? It's kind of a classic example of increasing returns. So, but which Bluetooth is for you? You've heard all these different Bluetooth this and Bluetooth that. Bluetooth low energy, perhaps. Or maybe you want to use Bluetooth smart. Well, haha, fooled you. There's actually only one Bluetooth. They all have these different names along the way, but Bluetooth is Bluetooth, no matter what kind it is today. So it's very good to know, very important. So how Bluetooth works. So Bluetooth, I'm going to put GopherBot down here. So Bluetooth, we're going to go over this entire diagram here that shows all of the Bluetooth low energy stack. No, just kidding. We're not going to go over all these details. Instead, if you want to know more about the very low level details of the Bluetooth low energy stack, check out SparkFun has a great introduction along with some others. But let's just talk about the roles of Bluetooth that you would use as a developer when you want to write some code that uses this Bluetooth interface. Well, first of all, we have peripherals. Peripherals like your mindfulness headset or your heart monitor. And then we have centrals. Centrals like your cell phone or your car. And so this is a cool diagram created by Adafruit. And it shows in the middle our centrals, like our mobile phone, tablet, computer, and then around it, surrounded by this embarrassment of riches of peripheral devices out in the world, all supporting Bluetooth. So in order to get started, we have to use the generic access protocol. So what does that mean? Well, when peripherals want to be found, of course, they advertise. So we're going to start with a demonstration that uses the Adafruit itsy bitsy NRF 52840, which is a Nordic Semiconductor NRF 52840 chip with a 32-bit processor. It's a 64 megahertz ARM Cortex M4, and it has about 1024K of flash memory. So let's take a quick look at our, here is the itsy bitsy. It's very small. You can see it. I mean, it really is small. It's a very, very cool board, and I use it for a lot of interesting things. So let's take a look at some code that we're going to use to program the itsy bitsy. So the code for the hello world of Bluetooth is advertising. So we can see package main, just like we would in any normal Go program. We're going to import the time package, and we're going to import the tinygo.org/x/Bluetooth package. And that's the package we're going to use to actually communicate with the device. So the first thing is that we have our Bluetooth default adapter. Since most devices only have one Bluetooth adapter built in, we have this shorthand for you. And so we're going to put that into our adapter. And so our main program, first we're going to enable the adapter. We're going to call this must function, so we don't have to check for the error repeatedly in this code to make it a little bit shorter. So first we enable the adapter, turn it on so we can use Bluetooth. Then we're going to create our default advertisement, which is whatever we're going to say out to the world. And then we're going to configure our advertisement so that its handler function is going to be able to provide this information that the local name is Go Bluetooth. Then we start advertising, and that's it. We're done. From that point on, all we have to do is just sleep for an hour and let the advertising take place. So let's go over to actually flash the code. So if I say make advertising, and I'm going to go ahead and plug in my itsy bitsy, and I'm going to plug it in here to my computer. And then from there, we can go ahead and flash it by running this make command that I've created. So it's going to, the program is 9K in size, which includes the entire Bluetooth access code and everything else. And so now if we take a look at our micro, then we can see that, in fact, nothing is happening. Right. Of course, because we need to actually listen to this. So let's go and unplug our device here, the itsy bitsy, and let's plug it into a battery. And that way, with this battery, it will start advertising again. And now let's put it aside for the moment, and we'll go on to the rest of our talking, which is, what about when centrals are looking for peripherals? We have a peripheral that wants to be found, but we do not yet actually have anything that is looking for it. So when centrals want to find peripherals, they scan. And so when they scan, we're going to take a look at the code here real quick of our scanning code. So let's see, get out of Zen mode. Whoops. There we go. And we'll go to our scanner. So the scanner here is actually very, very similar to the code that we wrote before for advertising. We have our main package. We import the Bluetooth package. Then we have our adapter, a default adapter, in this case on my computer. And then we have to enable that adapter in our main function, turn it on, and then we start scanning. So when we turn on our scanning, we have our scan handler here. Wait, something's missing. There we go. So once we start scanning by calling the adapter.scan, we pass it our scan handler, which is the function that's going to be called whenever a device that we find is located. And that scan handler here gets passed the adapter. And then it also gets passed the scanned result for each time. I think we can turn off the speaker. Vamos a quitar los altavoces. So then the device has got a string which corresponds to its address, and then also the relative signal strength of it, since you've probably seen this before, devices that are closer or further, and then the name of the device. So let's go ahead and run this by saying make scan. And you can see here, Go Bluetooth is showing up. That is our actual device that we flashed before. So if I unplug it, it'll stop showing up. And if I plug it back in, it should, if I can plug it back in correctly, there we go. You'll see that it will appear again. You see how fast a microcontroller boots. It's very, very fast. All right, so now that's our scanning. So, and then what happens? Well, once our central has found our peripheral, they connect. Oh, isn't that cute? By the way, there is no actual contact between centrals and peripherals. That was a metaphor. All right. So, but let's keep the metaphor going a little bit longer since we're in the mood. Connections are exclusive once they're made. I mean, for the lifetime of the connection. So if you disconnect, then your new connection will be exclusive. And of course, once you're connected, that's when we ask the big question. What data do you have? So for that, we're going to need the generic attribute protocol, or GATT, which is the other main category of protocols when using Bluetooth. So we have services, and each of those services has a unique identifier so that it's unique in all the world for that one service. And then it has a list of the characteristics. For each of those characteristics, it also has a universal unique identifier, and then the actual data. So if we look at this cool diagram that was created by Adafruit, we can see here that we've got a service and a bunch of characteristics under it, and then a different service and a couple of characteristics under that. And so this defines pretty much the whole high-level standard of what we care about when we're using Bluetooth, low energy. The process of figuring out what that data is actually called discovery. And we don't have time right this instant, but what I thought I would show you, since we don't have time to look at the code, I brought another toy with me so we could go back to some scanning. This is an Adafruit clue board, which has another NRF 52840 semiconductor, Nordic Semiconductor microcontroller. And then we're going to plug into it with just a battery. I flashed this code earlier. And I could plug it in here real quick. Then you will see that as it boots up, we can actually, that's a little out of focus, but you can see it scanning, and you can see Go Bluetooth appearing on the display of this device. So a microcontroller can be a peripheral, or it could be a central, right? So we'll just leave that running. And so there are well-known services and characteristics that are out there defined by, of course, the Bluetooth Special Interest Group, of which Nordic Semiconductor and a number of other countries are, or companies, I should say, they're all members. So these well-known include, for example, the battery service. If you've ever been in your car and you wondered, how does your car know that your phone is on low battery? It's because of the battery service. There's the location and navigation service, which would be the opposite, how your phone knows that the car's GPS is working. And then the heart rate service, which is if you were going to connect a heart rate sensor, this is how you would be able to do it. So let's actually take a quick look at a heart rate sensor. We're going to use the Adafruit Circuit Playground Bluefruit, which is another board from Adafruit, awesome company. And it just so happens that's the board that's built into GopherBot. So what I'm trying to say here is we're going to use GopherBot now. GopherBot, do you have a heart? Well, GopherBot does not have a heart. However, GopherBot can have a heartbeat. So let's take a real quick look at that code. So the heartbeat what we're going to do here is the same pattern as what we saw before, right? Let's see, Control KZ for Zen. So we have our package main. We have the standard packages from Go, Rand, and Time. We're using the Bluetooth package. Once again, the default adapter. And this time we have a characteristic, which is the heart rate measurement. So we enable our adapter, same as the other demonstration. We create a default advertisement, same as the other demonstration, the advertiser. But this time, our advertisement options include the local name and which one of the service UUIDs that we're going to actually advertise that we support. In this case, we're going to say we support the standard service UUID for heart rate, which is a previously well-defined, well-known UUID that's any heart rate monitor will support. So we start advertising, and then we're going to add our services. The Bluetooth service has the Bluetooth characteristic for the heart rate measurement. So this is the actual data itself. And we're going to start with a heart rate of 0. And we're going to set this permission, which says we can receive notifications from the device. This is how Bluetooth Low Energy is so efficient. Instead of continuously asking a device, do you have new data? Instead, it receives a notification from the peripheral device saying, here's your new information. And then we're going to start the heartbeat. So the heartbeat, it's going to check the time, and then we're going to show the pulse somehow by flashing some lights. We're going to sleep for however long our heartbeat is supposed to wait for, and then we're going to vary it between 65 and 85 beats per minute, which I've heard for a Gopher bot is relatively normal. And then last, we're going to write this to the characteristic, which is going to send the information from the peripheral to whatever centrals are listening. Okay, so let's go and let's take a look and let's actually run this code. So we're going to say make heart rate circuit play. And so I'm going to plug in GopherBot. Don't worry, GopherBot, I'll put you back normal afterwards, but right now we need to program you so you've got a heartbeat. So let's plug in and then we'll flash the board. This is only a 13K program, a lot smaller. And now we can see actually that GopherBot's heart is rotating at approximately every second, depending on how fast or how slow. So let's unplug from the computer and let's plug in the battery. That way you believe me that, in fact, I'm not faking this. It's all real. So we're going to plug in GopherBot and, oh yeah, let's take a look and see if we spot in our scanner. Yeah, we could see that we've got Go Bluetooth still. And then we've also got Go HRS, which is our heart monitoring service. So just to prove to you, though, that in fact, this is completely standard, what we're going to see is we're going to demonstrate this using, if I go back to it here, using the heart rate monitor that we're going to show is using Android. So I'm going to plug in my telephone here, and let's go over to the Linux. I'm going to plug in my phone, and then what I'm going to do is I'm going to run a program that's called screen copy. Whoops. Oh, yes, I have to permit. And then let's try running it again. Okay, so now you can see my Android phone has appeared now on the screen. So if I go to this application from Nordic Semiconductor called the NRF Toolbox, it supports a bunch of very well-known services, and one of them is the heart rate monitor. So if I connect here, we see Go HRS is listed under the devices. So if I connect to it, and we can see here's my heart rate coming through. Actually, it's not my heart rate. It's actually GopherBot's heart rate that's coming through at the same time. So GopherBot has a heart. That is so awesome, right? Who knew that robotic plushies could have a heartbeat? Okay, let's keep going because we have little to do and lots of time. No, wait, strike that, reverse it. So there are also custom services and characteristics, not just the well-defined ones, but that usually big companies get together in their consortium, but there's lots of other devices in the world. And for all these other devices, for example, like drones. So I, of course, love flying drones, and I've never found a drone I didn't want to fly programmatically. So we're going to build a TinyGo flight controller. So the first thing is that we're going to use a Parrot Mambo mini drone, which if you've maybe seen a couple of my talks, you see that I love these little Parrot drones. They're very inexpensive. They're very cool. Kind of hard to see in that angle, but so this is also got a 3D printed enclosure with a first-person video camera. So let's go ahead and turn this on, and you can see that the eyes are going to start flashing red because it's waiting for something to connect to it. Okay, so what are we going to connect to it? Well, for that, we're going to use, once again, the same chip that we used initially, the itsy bitsy NRF 52840. So this is a very, very cool little board. And I used it in order to make this, which is a small flight controller with only one joystick. So it's hard to fly a drone with two joysticks, but I'm going to do it with only one because that's the most minimal possible flight controller I could think of. So let's take a quick look at the code. So there's actually two pieces of code here. The first one is that we're going to go take a look at the drone client code. Now, keep in mind here that the drone is a separate Bluetooth device with its own firmware, and we're not reprogramming that firmware. This is actually the client that we're going to use. So it's a client wrapper from the flight controller as a proxy for the drone itself. And we can see here it's got a main, oh, sorry, wrong code here, wrong code. Let's go back to the mini drone. It's in the other one. My bad. There we go. Okay. So this is the mini drone code, and it's got a few different services and characteristics that it defines based on the not well known, but having these UUIDs, which are defined by Parrot. And so it's going to be a wrapper around the Bluetooth functionality. So when we say new mini drone in our code, we're going to pass it the actual Bluetooth device that we found. And then based on that, when it starts, it's going to discover the services. Which ones? The services we use to fly the drone, of course. And then once it's found those, it's going to discover the characteristics for each of those services. First, for the command characteristic, which is what we use to send commands to the drone, like take off and land. And then the flight status characteristic, which is how we determine, is it flying, has it crashed, etc. And so if we go take a look at the other code that I was trying to show you a minute ago, which was the actual flight controller. The flight controller is what's running on the itsy bitsy board itself. And for that, it looks a lot like the code that we've seen previously. A few differences, because this particular board, we have, as I showed you before, we have a display. It's an I2C SSD 1306 display. So it's just a very, very small little LED OLED display, an analog joystick, and of course the buttons, right? So if we go back to our code here, we can see we are initializing the I2C interface just so we can look at the display. And then the important part is that we're doing the same thing as what we did in our other Bluetooth code, right? We're enabling our default adapter. We're scanning. In this case, we're going to scan for the drone's MAC address, since every Bluetooth device has its own MAC address, so we can find it by that. We're going to connect.
All right, seems like we have an intermittent connection right now. Let's see. We'll give Ron a few minutes to kind of come back on. Well, yeah. I don't know, I guess this is the dead air that's so complicated to fill. But first and foremost, while Ron gets himself situated, I want to thank everyone for joining us today. And for those that are staying up late, thank you for, for staying on with us. I think it's been an awesome event so far. Lots of great talk, lots of great content. All the videos, as Angelica said, who unfortunately had to jump off early, will be available for playback later on today. So, see if I get Ron to jump back in on the Zoom channel. 1 second, put myself on mute. Cool. All right, everyone, just a quick heads up. We're just waiting for Ron to jump back in if he's able to reestablish his connection. So I'll give him a few minutes to, oh, there he is. Ron, welcome back.
I don't know what happened there. From our side, everything looked fine. That's a bummer. Sorry, where was I?
You were just in the middle about to unplug some hardware device, and then you just cut off.
Oh, well, yeah, but do you know which one?
You were telling us about the joystick and the drone.
Ah, okay.
Yeah.
All right, excellent. So right now we should be connected. If I flash the code here, it should flash the board with the right code. Am I still coming through okay? Hopefully.
Yep. All good.
So I've just flashed the flight controller with this latest code. And so if we go over to the micro camera, we can see that it's actually displaying the joystick. And so theoretically, I am connected to the drone. So now if we go over to the drone's camera, you can see that actually this is the drone's eye view, and here's my flight crew. So let's try the takeoff and see if it works. So I'm going to press the takeoff button. It's not the best connection, maybe. It's a little interference, but I think we'll be all right. So I'm going to press the takeoff button and let's see what happens. Okay, and we're flying. So we're actually sending the Bluetooth commands from the drone. And if I press this other button, I can hopefully get some height. So you can see that, in fact, I am here. We'll flip around. The video is a little odd quality, but yeah, there I am. Hello, people of the internet. All right, so this is the drone that we're flying entirely through Bluetooth, and it's actually almost out of battery. That's why its eyes are flashing at me. So I guess we better land. Oh, just in time. We've lost video. We've lost contact with the probe. What does that mean? Well, it means that our demonstration is over of the drone. All right. Well, I hope that worked. So, in conclusion, no contact with other physical objects or living beings? Well, no problem, of course. All you need to do is go without wires. So please check out tinygo.org/Bluetooth. That's where you'll find the information about Go Bluetooth. Runs on Mac, runs on Linux, some very initial rudimentary Windows support, and runs bare metal on microcontrollers. And with that, I will say thank you so very much. And are there any questions? I don't know if I can hear.
That's it. Awesome. Well, we can hear you, Ron. First and foremost, thank you. Amazing talk, as always. You do a great job presenting, hardware in such a fun and cool way. So thanks for that. I'm going to do a quick spot check across all the channels to see if we have any questions for you. Let's see. Lots of kudos on the setup that you have going there in the basement and all the cool hardware.
Oh, thank you. Thank you.
Yeah. But I don't see any questions.
Everyone's just stunned. They're like, wait, is the drone okay? Is Gopher not going to get reprogrammed? I mean, is this a cliffhanger ending? Actually, it is. And so this is just episode 1. Tune in later this year for the sequel, Go Further Without Wires, which will all be about Wi-Fi and TinyGo. So this was just episode 1. Or episode 4, I don't know how you people count them. But
well, awesome stuff, and well, that's good to hear. We actually, a question just came in as you was promoting the next episode. The question that we have is, does the Go Bluetooth work on ESP32?
So, does Go Bluetooth run on ESP32? And the answer is no, not yet. So the ESP32, we have a couple of different modes. So the ESP32 is a very cool little chip, which is probably one of the most popular Wi-Fi chips, especially because of its predecessor, the ESP8266 was like the first less than $1 microcontroller that had built-in Wi-Fi. So the ESP32 is its successor, and it has a built-in Wi-Fi as well as Bluetooth. So TinyGo supports this chip in 2 ways at present. One is that you can use it as a coprocessor. There's a lot of devices which have a built-in ESP32 in addition to whatever other microcontroller. That way, the main microcontroller can be handling the logic and the ESP32 can be doing the Wi-Fi or the Bluetooth. The other way is that we can actually run TinyGo directly on the ESP32 itself. But there's currently limitations for both of those when it comes to Bluetooth. The first one is there is some really cool software that runs on the ESP32 called Nina. The Nina firmware is originally from Arduino, but it's been greatly enhanced by Adafruit. And it lets you use a serial peripheral interface or a SPI interface to communicate from your main microcontroller to the wireless chip. And the latest versions do support Bluetooth Low Energy. So we're going to add the support for that to Go Bluetooth so that you can use an ESP32 coprocessor from some chip that doesn't have wireless built in, like your ATSAM D51 or ATSAM D21, which are also really popular chips from boards made by Adafruit and by Arduino. So the other one is, can we actually run it all on one chip? And to do that is quite a lot trickier because quite a lot of the SDK that's created for the ESP32 is not open source, unfortunately. And the parts that are all written in C. So we're currently working, a few of us, on figuring out, can we use parts of the C, under their license? Do we want to include a lot of C wrappers? I mean, we're already doing that for the Nordic Semiconductor interface. So I don't really have a problem with that at all myself. It's more there's quite a lot of technical work involved, but we're really just getting started with the ESP32 chip, but quite a few people want to use them. They're very inexpensive and popular and very powerful. So we're working on it.
Awesome. There you have it. Work in progress, y'all. We have a few. Yeah, it always is. Seems like we kind of people's perked up a bit. We have a few more questions if you have the time.
Sure.
Before we call it a show. We have how was the drone? This question's coming in on Gopher Slack. How was the drone broadcasting its video? Or was that through Bluetooth as well?
So So no, it was not. It was not broadcasting through Bluetooth. So this drone doesn't actually have a camera. Not normally. I have a 3D printed. So the parent Mambo has actually a built-in little pellet launcher and a little dropper, and they're controlled through electrical connections. So they're right on the surface through a Lego compatible connector. Yes, all cool flying things need Lego compatible connectors. Attention, drone companies. So this is a first person video camera that is plugged into this little 3D adapter, primarily so it can draw power from the same power without having a separate battery. And so I just plug it in, and I have a separate, I have it over here somewhere. Oh yes, there we go. So I actually have a separate little adapter, wireless dongle that I plug in. That's a supports video for Linux, obviously. So, but it's just a normal video capture device. So you plug this in, and then you can just stream your video. And it's very fast because it's analog signals that are sent with the video. So when people are flying first-person view drones, they're not using digital video. They're using analog video because digital video, the latency, you'll crash your drone. I may crash the drone anyway, but for sure you'll crash it.
Oh, awesome. Seems like the response was analog wins. So really good
Yeah,
stuff.
no, do not forget about the analog of our fathers.
With that, Ron, I want to say thank you again for such an amazing talk, and also to all our speakers that came before you. Thank you. Awesome, fun event. I found myself just like in awe of all the stuff. So thanks again for your time. I'm going to thread the rest of your questions, like 2-3 more questions. I'm going to thread them in Gopher Slack so you can get to them, when you have some time later. And the video will get played and it will be available on YouTube. So I wouldn't be surprised if more questions pop up later on. So again, thank you for your time. With that, I want to go ahead and wrap up the event and say, once again, thank you to all the attendees for making this thing happen, for joining us today. And also a big shout out to our speakers and our lovely my lovely co-host, Angelica, who had to jump off a little early today. For anyone who's interested in getting involved in any of the GDN events, please reach out to myself, Wilken at GoBridge.org, or Angelica at GoBridge.org, and we're happy to work with you and see how you can help us contribute to make this event even better. For those that joined in on the book giveaway earlier today, I have all my 13 responses, so thank you for that. What I'm going to do is I'm going to be sharing your email with Pack Publishing, who will be coordinating the ebook distribution and the 3 physical books that need to be sent out. If I'm not mistaken, there's shipping restrictions to Europe, UK, and the US. So I'm sure they'll work out all those details when you hear from them. If anyone has a problem with me sending their emails to Pack Publishing, just send me another email saying no, and we'll figure something out there. All right, so that's a wrap. Thanks again, everyone. Really appreciate it. Ron, any last few words before we cut the stream?
I just want to say thanks to everybody. Fantastic job organizing. Fantastic job from all the speakers. I want to say thanks so much to my technical staff here at La Pipa, and have a beautiful and wonderful day, and stay safe out there, everyone.
Awesome. All right. Thank you. And with that, farewell, folks.